Good morning, everybody. Ooh, it's partly off my ear. Makes me sound like I'm talking in a plastic bag or something. All right. Well, happy Friday. Woohoo. Weekend starts in 50 minutes. Anyway, just gonna get distracted. So, where are we at? I think we left off. Here is my recollection. Bring that up. Okay, so let's try and remember how I covered it yesterday, if that gives me any clues. So, as we said on Wednesday, being able to figure out the probability of events is pretty useful in genetics. One reason is that essentially that's what allows us to make predictions, right? If we are carrying out a cross according to Mendelian principles or inheritance, then we can make predictions as to what we expect, right? And so those predictions can then serve as like a yardstick, essentially. I'm not sure that's a very useful term anymore. Don't know, meter stick, yardstick. I guess yardstick's still used. Anyway, of whether or not what we actually see is close to what we predict, right? So it's kind of an extension of that theoretical framework that I was talking about a while back when we started on Mendelian genetics. It's also kind of everyday sort of practical use too. I mean, if not really so much in our daily lives, right? But if you were a genetic counselor or if you knew that you were a carrier for a particular disease, then this is an important consideration. You need to kind of weigh up the risks of your offspring potentially having or expressing a particular phenotype that you wouldn't want them to have, right? So that's kind of the practical application of this sort of stuff. Oh, just before starting, obligatory puppy shot. There she is in her usual spot. And big sigh. There's the other one. I am surrounded by dogs, which is a nice place to be. Okay, so when we talk about events, we're really concerned with, are those events independent or are they mutually exclusive? And what we mean by independent is the probability of one event happening or the outcome of a particular event has no effect on the outcome of another event. All right, just type that down. So a classic example of that is sex of your children. Right. So if you have a boy for your first child, then whether or not you have a boy for your second child is completely independent. And so I like to think about this, thinking about it in terms of gambling, essentially, right? So I don't know if any of you play the lottery. I don't. I tried it a few times in the UK when it came out, and I think they said it was one in 10 odds of winning £10. Right? I was like, all right, well, so I think I spent £10 and I didn't win anything. I was like, that sucks. I'm not going to do that again anymore. Seems like a waste of money. But anyway, so winning the lottery, you have certain odds, right? I don't know what. I don't really follow it very much. So say it's a kind of 1 in a million chance of winning, the big prize. Now, what's the likelihood that you're going to win 2 different lotteries? Is it going to be the same, 1 in a million? Is it going to be 2 in a million? Or what? What's the odds of winning both of those lotteries? Is it going to be the same as, larger, or smaller than winning 1 lottery? What do you think? Anybody? Are you there? Oh yeah, people are there.
Can you repeat the question, sir? I couldn't hear you.
Sorry, muttering to myself. What are the odds of winning 2 different lotteries, top prizes? Are those odds going to be the same, larger, or smaller?
Larger, probably like 1 quintillion something.
So that's a good kind of point. The number at the bottom is going to be larger, right? The denominator. That means the odds, or the probability, is going to be smaller, right? And the reason for that is that you multiply the probabilities of those 2 events together, right? So if the events are independent, you multiply their probabilities together to get the probability of both occurring. And so when you multiply fractions, because it's kind of in some ways easier to deal in fractions. So let's say you have I don't know, 1 in 10 chance of getting a free prize when you open box Crispies. If you want to get 2 free prizes, probably this is going to be 1/10 times 1/10, right? And so when you multiply fractions together, you multiply the number at the bottom, right? So this is going to be 1/100, for example. Right, so remember, when you multiply fractions together, you multiply the number at the bottom, which is essentially what, I don't know actually who was speaking because it doesn't show me, what you meant by the number's going to be larger, right? It's going to like 1 in a trillion or something, trillion. That's exactly essentially what you were kind of getting in your head. There's put more formally here, right? So if you have a 1 in a million probability of winning the lottery, and you want to win both lotteries, either 2 with the same odds, it's going to be 1/1,000,000 times 1,000,000, right? Which is obviously a really big number. I don't even know what that is. I know. Can work that out in my head. Okay, so how can we use this in a kind of practical application, right? So let's say, these kinds of questions I give you on the exam. Question. 2 parents are both carriers for a recessive disease. What is the probability that any child they have will have that disease? Does everyone know what carriers mean in terms of human disease? What does the word carrier mean?
Oh, like you can have it but not show symptoms, like if you had the malaria carrier gene. I mean, not the malaria, the sickle cell carrier gene.
Okay, so you're all right. You have it, but you don't explain it. But why? What is the genotype of that individual? So what's
Heterozygous.
yeah, exactly, heterozygous, right? So you have a recessive allele for that gene, but you also have a dominant allele which masks that. So you never see the recessive allele. Okay, so back to the question. What's the probability that any one of their children would have that disease if they're both heterozygous? Yeah, exactly, Stephanie. 1 1/4. Why? Why 1 1/4?
Because it's recessive, and if they're both heterozygous, it's always gonna, and it's just two traits like that. It's always gonna be 1 of 4.
Yes, not 2 traits.
I mean, 1 trait, yeah.
Yeah, 1 trait, 2 alleles, or as Stephanie put it, is essentially the F2 of a monohybrid cross. Right, same kind of deal. Okay, so question 2. What's the probability if they have 2 children that both will have the disease? Almost definitely. You're on the right track, but the math is wrong. Remember what you're doing to the denominators. It's up there on the screen in front of you. Yeah, exactly. You multiply them together, right? Yes. So you have a 1 in 16 chance of having both children with that disease. Okay, let's add a like extra wrinkle. Two parents are both carriers for 2 diseases or different diseases. What's the probability that both of their children have both diseases? All right, so there's a couple of different things here. This is actually what I'd call a kind of one of the more challenging questions you get on an exam, because you've got to work out 2 different bits of information to get to the right answer. So the first thing you need to do is figure out what's the probability that any given child will have both diseases. So do that first. What's the probability that any given child will have both diseases if the parents are heterozygous for both genes? Again, I'll give you a hint. It's kind of essentially the Stephanie's answer further up as to why the other question was 1 in 4. We'll give you a clue. Dealing with 2 traits. Both parents are heterozygous for both genes. What are we actually looking at here? What kind of cross? It's dihybrid cross, right? So what's the probability of getting the double recessive in the F2 of a dihybrid? Karen, you should all know the ratio. Yeah, 1 in 16, exactly. So that's the first part of your question. Now you need to use that to calculate the second part. What's the probability if they have 2 children, both children will be homozygous recessive for both traits? Almost. Hang on, I'm going to stop screen sharing so I can use my calculator. Ah, yes, someone got it right. Someone's too fast. Exactly. Who was that? Let me see. Yeah, Stephanie, it's 1 in 256. Because again, and so Sarah, you're again doing what someone else did earlier, which was adding those together. We're not adding together the fractions, we're multiplying them. And so when you multiply them, and this is worth stating again, when you multiply fractions, you multiply the denominator. At least for essentially things that are 1 over something. It gets a little more complicated otherwise. I'm not going to get into that. And I wouldn't give you examples of that either. Right, so the answer is 1 in 256. Okay, so this is just to kind of get you thinking, right? What's the probability of a particular outcome? Right, and if these events are independent, then what's the probability of getting 2 of them, right? So you can go into this all over the place, right? So, another question. And really, I want to just give you these because these are the kinds of questions you're going to get in the exam, right? So I want you to get used to thinking in this kind of way, right? So you understand it. So I don't know what question number we're up to now. Both parents are carriers for one disease trait. What's the probability that of their 2 children, one is a carrier and one has the disease? Again, still working around the same kind of stuff that we were talking about earlier. It's the thing about monohybrid cross and the genotype ratio. What's the probability that you'll get a homozygous recessive? We've already done it further up. All right, exactly, Brianna. And Stephanie, you got it correct. Okay, so how do you turn that into probability both? Exactly, Sarah. It's going to be 1/8 because it's going to be 1/4 for the disease times 1/2 for the carrier. And that's 2 times 4 is 8. All right, you got it. Good job, everybody. Awesome stuff. Okay. So again, this is just another way of thinking about stuff. So you have to get your brain into the right track to think about it in that particular way. And doing these kinds of practice questions is a good way of doing that, good way of practicing it, essentially. Okay, so that's one type, right? So that's for independent events where the outcome of one event has no effect on the outcome of another event, right? And generally speaking, phenotypes are independent events. Okay. So next up, mutually exclusive events. Basically, if you have one outcome, you cannot have a different one. So if you're rolling a die, for example, and you get a 6, you can't get a different number because you got a 6. Similarly, if your first child is a boy, it can't be a girl because it's a boy, right? If something occurs, it excludes the possibility of other events occurring, right? And so another way of thinking about this is, again, gambling, right? Because gambling is all about odds, if you think about it, right? It's a matter of probability in most cases. Some skill for like card games and stuff. But think about it in terms of odds in horse racing. My granddad used to bet on horses. I tried it once, didn't win anything, but as you can guess, I'm not a betting person. But he used to love kind of going through the paper and like highlighting horses and stuff. So if you go to a horse race and for any particular race, you bet on 2 horses. All right, I don't know, Stella Nag and Trotter's Favorite or something. Only one of those horses can win. Only one of the horses in the whole race can win because there's only one winner. So the probability of one of your horses winning is higher than one alone. Does that make sense? Who's that? Someone's at the door. Hello, love. I certainly am. There you go. You can say hi. There you go. Dogs are happy now. So the probability of one of them is higher, happening is higher than them separately. So you add the probabilities together. Hey, get off, mush. Oh, yes, sorry, puppy's trying to get me to rub her belly. So, for example, in the case of the Stella Nag and the Trotter's Favorite, and then we have Stella's Nag coming down the road. We'll go Stella's Nag. So let's say Stella's Nag is a 1 in 10 favorite. And what was the other one? Trotter's Favorite. Get out of it, dog. Is, oh, let's say that's 1 in 10 as well. Perhaps they're pretty equal horses. I don't know. Hopefully you're all following along rather than just like rolling your eyes around in circles. So probability, oops. I hate typing out probability. Yeah, there you go. I hate typing out the word probability. It's kind of funny because I have to do it so often. Of one of them winning, because I both can't win, right? You know, I guess you could technically have a dead heat, but for our purposes, only one of them can win. Then the probability is of one of them winning is those 2 probabilities added together. Now, when you have addition of fractions, you add the top numbers. Don't do anything to the bottom numbers, you add the top numbers. So it's 1/10 plus 1/10. Again, distracted by a dog. Equals 2/10, which is essentially 1/5. Right, so the probability of one of them happening is higher than either one separately, which kind of makes sense, right? Because you have essentially two cracks at the whip. Does that make sense for everybody? No, not 3/20, Caitlin. 2/10. Do you get why? So when you're adding fractions together, you only work with the numerator, the number at the top. So for example, if you had oh no, it's okay. But either way, if it was 1/20, it would be, oh, let's use that example. That would be 2/20 or 1/10. So same kind of idea. You can do with whatever. 1/5 and 1/5 is 2/5. You can't shorten that down because you can't divide 5 by 2, but the same kind of deal. And so the point here that's worth making in terms of biology is genotypes are mutually exclusive. So if you're heterozygous for a gene, you can't be homozygous dominant for that gene or homozygous recessive. Whatever your genotype is, it excludes all other possible genotypes. And you can see that here. Okay, so essentially, if your the probability of these two different traits having a particular genotype is going to the probability of having one of them times the probability of having another. So now the probability of having those two different independent things together is 1/16, because it's a quarter the probability of being homozygous dominant, pardon me, times a quarter of the probability of being homozygous dominant for the other gene, because those two separate traits are independent. At least according to the law of independent assortment, what you have for one gene has absolutely nothing to do with what you have for a different gene. So the probability of having a combination of genotypes like this, or this particular phenotype, is 1/16. Now there are, 4 different ways in which you can have a round and yellow P. You could have this genotype, or this genotype, or this genotype, or this genotype. So there's 4 different ways in which you can get the same outcome, right? And so these are mutually exclusive. If you're double homozygous dominant, you can't be, where's the heterozygous? You can't be double heterozygous, right? So you have 4 different routes to routes, I guess, to the same outcome. That is a round and yellow P. And so you add those probabilities together. And so if you actually add those numbers up, it's 3, 5, 9. So that's the 9/16, or the 9 and the 9 to 3:1 ratio, which is for the double dominant phenotypes. Does that make sense? The different phenotypes are, or the different traits are independent. So you multiply their probability together. The different genotypes for the same phenotypes are exclusive. So you add those together instead of multiplying them. How's that going? We can actually use that to kind of go through orders of events, right? So, and this is kind of laid out down there as well, but we'll go through it here. What we're up to now, question 4, I guess. Oops. What's the probability of having 2 boys and a girl? Total of 3 children. So first, what you need to do is think about how many different ways can you have 2 boys and a girl? I'll give you a starter. You could be boy, boy, and then girl. 3, Caitlin. What are the other 2? You're correct. What are you doing? Why is throwing something on the floor? Yes, exactly. Right. So it could be girl, boy, boy, or boy, girl, boy. Okay. Same as what Sarah put. So, sorry, I'm a little bit, I haven't had any coffee yet. That's why I'm speaking slowly. Well, wait, get down off of there. She's discovered that she can get from one couch to the other just by going over the divider. She's such a pain in the ass, that dog is. Okay. Back on track. Focus, focus. Only 17 minutes till coffee, plus brewing time, obviously. Okay, so focusing again. What's the probability of any one of those? So what's the probability of getting what Sarah put? Hang on, Stephanie. No. Let's work out this way first. What's the probability of having, if you had 3 children, of having a boy and then a girl and then a boy? No. Stop guessing. Work it out. What's the probability of having a boy? Is what? What's the probability of having a boy? If you have a child, it's either going to be one or the other. It's a half, right? So does the probability of having a boy affect whether or not you have a girl for your second child? No. So those are independent events. You have 3 independent events. So it's going to be a half times a half times a half. Right? Which is what? Both of those work. 0.125 or 1/8, right? Because it's 2 times 2 times 2 is 8. Top is still 1, so it's 1/8. So the probability of getting that specific birth order, well, actually, which one did I use? Yeah, boy, girl, boy. There you go. Thanks, Sarah. I can only see like a tiny part of the chat, otherwise I can't see anything else on my screen. So we've got 3 different ways of getting the same outcome of having 2 boys and 1 girl. So if we have 3 different ways, right, what do we then do? Oh, actually, skipping ahead a little bit. What was that? That was boy, boy, girl, or girl, boy, boy. No, he jumped in ahead. This each have the same probability. You'll see what I'm getting at in a second, Kate, I promise. Exactly. Oh, yes, that's right. Be 1/8. So, what's the probability that out of 3 options, I guess, possibilities is probably the better word. Now, what are we talking about? So, for any given birth order, sex of each child in series 1, 2, and 3 are independent events. Now, we have 3 different ways of getting the same number of children of different sexes, 2 boys and a girl. So how do we deal with those probabilities if they are independent, if they're mutually exclusive events? Right, if you have a boy and then a girl then a boy, you can't have a boy, boy, girl, right? Because they already have their sex. No, that's for independent events, Sarah. Now we're talking about mutually exclusive events. That's right. You use the addition rule. Essentially, you have more than one shot at the same thing. Yes. Thank you, Brianna. You add those together. So it's going to be 1/8 plus 1/8 plus 1/8. Dang it. Got to make sure I get this stuff right. Otherwise, it won't make any sense. And that, as Brianna put, is 3/8. Right. So hopefully, and this is one of the main reasons for, because I don't know, I'm not sure I could give you a good example of why you would use this in real life. It's just kind of like a fun thing to do. But it's a good way of illustrating the difference between independent events, where one event has no effect on the outcome of another, and mutually exclusive events. If you have this one, you cannot have this one. Right? So if you have 2 different ways of getting the same outcome, you add the probabilities together. Does that make sense, everybody? Cool. And there will be guaranteed, without a shadow of a doubt, questions on this kind of stuff in the exam. You know, if you have particular genotypes of parents, what's the probability of getting X, Y, and Z in the offspring? You know, those kinds of stuff. All right. So, sorry, doggy, I have to give you a stroke later. These probabilities kind of give us a framework, right? We predict that if Oh, I'm sorry, Sarah. Yeah, I think I got myself confused myself. Sorry about that. That was my fault. Where was I heading at? Yeah, so this is a way of predicting what if biology followed pure mathematical principles you would expect, right? But as you know, biology does not follow pure mathematical principles, right? There is noise, just random fluctuations and random chance, right? Same as if you flip a coin twice, you should get one head and one tail, right? You might get two heads, you might get two tails, right? The more times you do it, the closer your outcome, your observed results will match what you expect, but it will never be perfect, right? Even if you get up to like 1,000,000 coin flips, right? You'll never have exactly 500,000 heads, 500,000 tails. It'll be very, very, very close to that, one hopes, unless like your thumb gets really sore. But it will never be exactly that, right? And that's kind of what you can see going on here, right? The bigger the numbers, the closer to your expected or predicted ratio. Predicted is kind of a good word in this case, that you may get, but still you're not exactly at a 3-to-1 ratio, right? Even though that's what's predicted by the outcome of the monohybrid cross. So we need to have some way of figuring out if that difference, right, however big that we observe between what we get and what we predict, is that difference meaningful, right? In other words, is it random noise or is it something going on, whatever that might be, a mistake in your assumptions or something funky, right? And so let's unplug that. So to do that, we're going to use a chi-squared test. Where's my pen gone? Ah, here it is. Let's move this a little bit closer. Uh-oh. We might have to use a different color. Purple. Who doesn't like purple? And we're not going to get through all of this in the next 6 minutes. So what I want to do is give you like the underpinnings, I guess, the principles of a chi-squared test. And if we get time, we'll go through the steps that you need to take to carry one out. And I like breaking things down into steps because it makes it easier to follow. And then next class on Wednesday, because we're not meeting on Monday because it's Labor Day, we will do some practice. And I will change the deadline of the homework, first homework, which has chi-squared tests in it, to next weekend, right? So not this Saturday, but the following Saturday, right? So you're going to have time to go through it and practice first. Okay, so essentially what the chi-squared test is asking is, the difference between what I predict, and we use the word expect in chi-square test, between what I predict and what I observe random noise by chance, essentially, or meaningful. So essentially an example here would be, say you do we taught our puppy to ring the bell when she wants to go out the door. So for example, if you do a monohybrid cross and instead of getting a 3-to-1 ratio, so you'd expect a 3-to-1 ratio. So if you observe 100 individuals, you'd expect 75 and 25, right? The two different phenotypes. Instead, you just get 100 of the dominant phenotype, right? So that's going to be a large difference between what you predict or expect and what you observe. And so almost certainly something funky is going on there. In this case, the homozygous recessive is lethal, let's say, for example. Right, so we would use a chi-squared test to see whether the difference that we observe from what we expect, is that just random fluctuation, like what we saw in the PowerPoint for those P crosses, or is it meaningful, right? Is it because something's going on that is not just random noise? That's really what the chi-squared test is all about. And so essentially, the chi-squared value, actually, let's put us on a different one. Essentially, if it's random noise, we'd expect a small difference between what we predict and what we observe. If something's going on, which is a very scientific term, we'd expect a large chi-squared value, or we would get a large chi-squared value. Now, what I want to do first, above all of this, is that we need to go through what significance means. And we only have a minute left. So I'm going to introduce this, and then we're going to have to go through it on Wednesday. And we have a catch up in the schedule, catch up session. So we'll most certainly be using that to kind of catch up on stuff, because we're spending a little bit longer on this stuff than is accounted for in the schedule. So p-value, some of you have probably come across this before, is, and this is really worth writing out, probability of getting that result, outcome, test, whatever, by chance. And so if, and I'm just going to finish this off because I want this to stick in your head for next week, right? Even though most likely there'll be many fun things like Labor Day happening between now and then, this is a super important part of all biology. So p-value of 1 equals 100% probability. It's chance. p-value of 0 equals 0% probability. Now, you never get a p-value of 0. You can get very close to it, but you can't get a p-value of 0. Hello, dog. No, can't eat that. So this is the thing that really makes this difficult to understand, because it's counterintuitive. The smaller the number, the more significant something is. The larger the number, the less we care about it, because whatever we're getting, it's down to random chance. Okay, I'm going to leave it there. We'll go over this in a little more detail on Wednesday, and then we'll go through the chi-squared test and have a few practices on Wednesday too. All right, so there you go. You have a puppy. Goodbye. Have a great weekend. Stay safe. Don't eat too much. And I'll see you on Wednesday.